As seen on this clip, a pendulum applying the law of conservation of energy is used to demolish an old building. When the wrecking ball swings at its lowest point, it has the higher kinetic energy and the lowest potential energy, and when the wrecking ball swings to its highest point, it has the highest potential energy and the lowest kinetic energy.
The law of conservation of energy states that in a system, energy cannot be gained or lost but transformed throughout the system. Energy is defined as the ability to do work, and there are only two types of energy in an ideal situation for the conservation of energy of a pendulum. Kinetic energy is dealing with the velocity or speed, and as an object gains speed, it gains kinetic energy. It is represented with the following equation: 1/2 equals mv squared. M stands for the mass of the object, and v for the velocity of the object.
Potential energy is a type of energy regarding position, and in a pendulum we are talking about gravitational potential energy because we are dealing with the height a pendulum might achieve. It's represented with the following equation: mgh, where m represents the mass of an object, g represents the value of gravity, and h represents the object's specific height. As an object gains height, it loses speed. Therefore, as an object gains potential energy, it loses kinetic energy and vice versa. In an ideal situation, the initial potential energy plus the initial kinetic energy equals the final potential energy plus the final kinetic energy. But in a real-life situation, the initial potential energy plus the initial kinetic energy equals the final potential energy plus the final kinetic energy plus any energy lost in a system, because energy is lost due to friction or other factors.
An equation was derived from a real-life situation, and the value obtained was v squared equals negative 2g change in h plus 2 times fd over d times 1 over m. In order to prove the conservation of energy law, an experiment was done in which we recreated a pendulum using a 3-meter string, then recorded the time it took for different masses to swing. Then we used these values to create this graph, which proved conservation of energy, since the results show that the graph that was recreated had a y-intercept of negative 3.6 and a positive slope, which correspond to the equation that was previously derived.